Welcome to the lesson of simple harmonic motion with example calculations. Before we talk about simple harmonic motion, what is an oscillation or a periodic motion? Oscillation is simply a continuous repeated movement. For example, a child's swing. The swing goes backwards and forwards through the same position over again and again. Another example of an oscillation is a movement of a simple pendulum. We call this type of oscillation using a special name, simple harmonic motion. The pendulum oscillates around a central midpoint, what we call as an equilibrium position. We usually measure the current position of a pendulum from the equilibrium, and this is called the displacement. The maximum displacement of the pendulum from its equilibrium position is called as the amplitude. And the time it takes to complete one complete oscillation is called the time period. Here you can see the force of the pendulum always directs the pendulum towards the equilibrium point no matter where it is in. This force is called as the restoring force. So what is restoring force? Restoring force is the force acts to bring a body into an equilibrium position. In simple harmonic motion, the restoring force is directly proportional to the displacement. Now we can write the equation for a simple harmonic motion using a proportional constant k. F equals negative k times x. K is a constant dependent on the oscillation system. For example, for a spring type oscillator, this is the spring constant. X is the displacement measured from the equilibrium, and this negative sign means the direction of force is opposite to the direction we measure the displacement or the movement. Spring with the mass attached at the end of it can be used to demonstrate simple harmonic motion. If we pull the spring and leave it, it will start to move forward and backward in a periodic motion. And if you remember the Hooke's law, which is the same equation as we discussed before, here the k constant is defined as the spring constant. Time period, or the time taken by one complete oscillation for spring system attached to mass m, can be given as this. The time period is directly proportional to the square root of mass m attached to the spring and inversely proportional to the square root of spring constant. And the time period of a simple pendulum is directly proportional to the square root length of the pendulum and inversely proportional to the gravity. Now let's try to solve few examples. Question 1. If a 500-gram train is attached to a pole by a spring with a spring constant 100 newtons per meter and made to oscillate horizontally, what force will act on the train when it is at its amplitude position of 8 centimeters from the equilibrium? Well, now we know F equals negative k times x, so we can substitute the given values in this equation. F equals negative 100 Newton per meters times 0.08 meters. So this will result in a force with negative magnitude 8 newtons. A force of 8 newton will act on the train and tries to pull in towards the equilibrium. So force is always opposing the direction of the movement, that's why we see this negative sign. This picture will help you to clearly understand this problem. The second question, how fast train accelerates while it is at the amplitude position? So according to the Newton's second law, we know force is equal to mass times the acceleration. In the previous question, we calculate the magnitude of force and we already know the mass of the little train. Therefore, we can substitute these values in this equation where minus 8 newtons equals 0.5 kilograms times the acceleration, and we can get the answer for the acceleration by dividing -8 newtons by 0.5 kilograms, which will result in a negative 16 meters per square second. The final part of the question is, what is the period of simple harmonic motion of the train? So now we know for a spring system, the time period is given by t equals 2 pi times square root of m divided by spring constant. So now we can substitute the given values. The mass of the train is 500 grams, which is 0.5 kilograms, and the spring constant was given as 100 newtons per meter. So once we calculate this, we will get a time period of 0.44 seconds. This will bring to the end of this lesson. If you like this, please subscribe and like for more videos. Thank you.